That walks in.
Yes, the little kid.
I had a picture of the kid when it got stuck.
All right, good morning. Today should be a lot of fun. Last hour, they literally were shocked that class was over, and they slowly walked out of here. We had a great time. So today, what we are going to do is we are going to talk about reactions. So let's first talk about our schedule coming up, just so you have a clear understanding. Is that today we are doing a reaction labettes demo for our labette on Friday. You have balancing equations due today. A lot of you have been handing that in. If you haven't handed that in yet, please make sure you get that in by the end of the day today. Tomorrow we're going to practice just writing formulas, so you're not getting anything new. Just you need to practice it. We'll be helping you with all that. And then Friday, you're going to be doing the back of the lab that you have from today. And I'm doing the front with you today. You're going to do the back on Friday on your own. You get to experience chemistry hands-on, and my job is to show you kind of how we're going to fill all that out as we go. New homework policy. So for some of you, you may have already realized this, is that in the past, and if this doesn't affect you because you always hand your stuff in on time, fantastic. But our old homework policy is that you got 25% of your homework. So even if you were a day late, you got 25%. Please understand, I understand what you're saying by, I had this done, I forgot to hand this in. And then the next question might be, why did I get late points? The answer is, because it was late. But I had it done. Well, I too had my mortgage check written and dated properly, but I didn't put it in the mailbox for 4 days. And the bank, that darn bank, fined me because I was late on their payment. It doesn't matter, it was late. So late or not, you gotta start owning up to the fact and realizing, oops, I didn't hand that in. But what we're gonna do is that if you have late homework within the chapter and you get it in before the end of the chapter, because that stuff is for that test, which most of you, this already still applies to you. If you do forget to hand something in, it's not like you wait a long time. It will be 50% of the points instead of only 25%. So a little extra bonus for you, encouraging you to get that done. If it's outside the chapter, you're lucky to be getting 25. Honestly, we could have gone 50 and then 0, but you'll get 25%. So it's only a positive for you. So if you do forget, it's not quite as drastic of a change, but just so you understand if you're confused in the grade book. Okay, so if you could, let's get out equations 1. I want to do one problem with you. You might already have it all done, but if you don't, I want to do one that's at the ending. Just quickly, so you have an understanding of how this works. So this orange sheet is going to be something that every time you're in the resource room or at home or in class and you're working on something, you should have this out. If you don't have this out, you're just making everything more difficult for yourself. So if you're like, I don't get this, I don't understand how to do this, you don't even have this out. Of course you don't. On the back, there's a periodic table, and on the front, there are 3 things. One you have seen, which is a polyatomic ion list. The other 2 you will learn from Mr. Blackford next week. We are going to allow you to have all your polyatomic ions. You do not have to memorize any of them, even if you had to memorize them from last chapter. The reason why is we want to make sure that you are understanding the material and not having that get in your way. So let's take a look at how I do this. Number 23. We're going to say this statement a lot. Every time I make a new compound, you got to check the charges. So by using a periodic table and by using the polyatomic ion, you can check these charges. So it says aqueous barium chloride. So I look on my periodic table and I find that Ba is a 2+, it's in the second column, and Cl is a -1. Every time I make a new compound, I need to check the charges. So by figuring that out, that's BaCl2. I crisscross, right? It said aqueous. So we do have to put states of matter on here. So AQ is for aqueous, and that's where we place it. It is like a subscript. It goes way to the lower right. It says reacts with, so that's my hint. You don't have to write this down right now, but that's my hint that I'm adding something. And it says potassium sulfate. Well, if I look on what I'm writing above can be in my head or on a margin. Oh, potassium's K plus, sulfate. Oh, that's on my polyatomic ion sheet. And I look it up and it's SO4 with a 2-. Those crisscross. So I have K2, SO4. And it said aqueous. If you put a little effort and a little extra stock in the first half, the reactants, you've already basically completed the second half. And I'll show you why. It says to form that's my arrow. Okay, now, all of the elements are still present. Chemistry, you can't start with one thing and end with something else. This is an alchemy. Conservation of matter. You have the same elements before and after. So now it says barium sulfate. You've already put in that time. You know that Ba is 2 plus. You know that sulfate's 2 minus. So I just put that together as BaSO4, and it said it was a solid. The other one says aqueous potassium chloride. I'm going to give you a big, huge red flag and a warning right now. Those of you that look at a problem and go, oh, it's a K and Cl, no, there's a 2 because there was a 2. You need to let go of what happened on the left and focus only on these things. Every time I make a new compound, I need to check the charges. So I would just put my K, which is a +1, and my Cl, which is a -1, together. If every element had every number from the left go over to the right, we would never have to balance a single equation. That makes sense. If you just blindly write numbers down from left to right, we would never have to balance anything. That said, that was AQ. We're almost done. So now, last step, very important, we got to balance the equation. Look on both sides. For those of you that look at it and feel like you got to balance it all at once, you're doing way too much work, just focus on one element. So the first element I see that's out of whack is the Cl, right? I have 2 here, I have 1 there. I'm not looking at everything. Do I need to show this work? I don't. It's only on that worksheet. So if I have 2 and I need 2, I put a 2 in front. So here's a little test right now. When you wrote this, did you give space? See how I have a little bit of space in front of everything? In the future, make sure you have a little space. What did that K, or what did that 2 just also do? It also got my K to be a 2, right? Well, that's good. That's a 2. And then I just double check some things. Ba, 1SO4, 1SO4, hey, I'm done. So most balancing is going to go pretty smooth. Hey, there's a 2 there, there's a 3 here. There's not a lot we have to do. So 21 through 25, you have to put the states of matter, and you need to kind of complete it, something like this. So we give you the states, we're telling you everything in there. What you need to start understanding is every worksheet we're going to take a little away by giving you even more. So, that being said, we are going to get into our notes today. So if you could take out your note sheet that says signs of a chemical reaction, or reactions, and then it says signs of a chemical reaction. We're going to get going. So there's a bunch of pictures on the tab. All right. You'll know later. In a reaction, or when you're in a lab, you have to know when chemistry actually occurs. When are we making something new? So a chemical change is when something new has been made. So we have 4 images on the top. If these things ever are present, or you observe them, then you know something new has been produced. And these are the observations that you're going to have to make over the rest of this year. So the first one is, these are some chains, and half the chains are rusted. If there's a color change halfway through the reaction, something happens and it starts to change color, that's evidence that a chemical change has occurred. We could have gas. You have bubbles coming up and gas. Now, these aren't always end-all, be-all, because you could get confused and say, hey, I'm boiling something and I see gas. Oh, it's a chemical change. But this is definitely a sign that there could be one. And if you know that it's a different gas than the compounds that existed initially, then you know that you, as they existed, and not a physical change, but it's a chemical change, you would have gas produced. The most popular one, the one that students love to see the most, is a lot of light. So that could be like a flame that's resulting from it, or you could be feeling the beaker or the test tube, and you could have heat. So a change in temperature, so light or heat. So those 3 things you guys have experienced a lot in your lives. You've seen things change color, you've seen gas come off of stuff, you've seen light and heat. I mean, a fireworks show right there. All in one. You get it all. The last one you probably have not seen. I would hope that you don't experience it too much. It's a precipitation, or when a precipitate is made. Next week in large group, you're going to see one on a larger scale. But it's when you take 2 solutions, and out of nowhere, like out of the blue, a solid, which looks more like a cloud of a different color, will just show up, and that's called a precipitate. So those are our 4 signs, and we're going to be using those today, and you're going to be using them on Friday, you're going to be using them on all of our labs. So here are some examples of those, just visually. You did this one in the either or lab. That's when you put that copper in to that solution and it changed color. This one's a great demo. It's nitrogen triiodide. It's a contact explosive. You touch it and it explodes. Later in the year, if you're in my room in mid-May, there may be signs around the hood that says "Don't touch contact explosive," because one of my AP students is doing that as a final project, and it sometimes explodes while people are in their desks. You're safe, but you jump a little. It's not quiet. Here's light and heat as an example, and then this is an example of a precipitate where nothing was there. They're not squirting the white solid in there. That was another clear liquid, and because of that, if that settled out and you let it settle, it would be like similar to like really fine white sand almost. It's not being sand, but that's a way to think of it. So let's talk about reactions. So let me take you back to my childhood. You guys are spoiled, and now some of you're probably too old for cartoons. But when I was a kid, we had a very small window. It was Saturday morning cartoons, and you had to watch it on a certain channel, not a channel called the Cartoon Network, because after a certain time, the cartoons disappeared and a really boring news program came on with adults talking about God knows what and things that I didn't care about, and then my cartoon viewing was over. And I watched the Smurfs and He-Man and the Thundercats and DuckTales, which is coming back now. That was good. But then the Flintstones. So I want to make sure you are very familiar. So we're gonna watch with this family, and we're gonna watch a little bit of the Flintstones. So this is the intro and the ending. Now, after you leave the movie theater, you get hungry. Flintstones, meet the Flintstones, they're the modern Pronto burgers. From the town of Bedrock, there are things right out of Look at that rib. Someday, maybe Pepper will win the fight, and that will stay out for the night. When you're with the Flintstones, have a yabba dabba do time, a dabba do time. We'll have a gay old time. Darn cat. All right, so let me tell you, let's talk a little soap opera, a little drama of a family here. So we have 5 different reactions. The more you understand about how reactions are constructed, the more you can predict what's made or what it was made from. So this man is Barney Rubble. He's a good, lighthearted soul. He's a fine man. And one day he met a beautiful woman named Betty Rubble. And they just hit it off, and they had chemistry. And they became one. 2 hearts became one beating heart. And they are separate in the beginning and then combined at the end. And that's what we call a synthesis. That's that type of reaction, when you make one thing from many. So a great example of this is something that we all experience. Billions of dollars worth of damage result from this, but rust, where you take iron and oxygen, and there's a little more complicated than that, but you combine it into one. So you have multiple reactants, and you have one product. Please understand that there could be 3 things. I mean, it's not always just 2 to 1, but there's always one. We are making one thing. So that's a synthesis. So if it's ever said the synthesis of whatever it will be, that would be making it on the right side, and then we put the reactants on the left. But you know, in every relationship, it takes effort, and it's hard. And sometimes things don't always go the way that we'd like. So as much as love was there, sometimes life gets in the way, and although they're smiling, maybe they're happier apart, maybe. So they've broken down. You went from 1, and now they're 2 again. And that is called decomposition. And you have experience with that, decomposing. in the woods. You can have a tree decomposing and plants that decompose, and a body in a trunk, and other animals that are in the woods just will break down. So an example of that is a reaction that's in an airbag. There's actually about 3 reactions that exist, but within that reaction, the NaN3 breaks down into its elements. Notice that the N is a 3 on one side and a 2 on another. Just keep reminding you that the subscripts aren't automatically assigned to each element. So every time we make a compound, we have to check the charges. We have to look at what is going on with that structure or that compound. So that's decomposition. And that should make sense that when something decomposes, it breaks down into many things. All right. Well, now it gets a little more tricky. So maybe they're at game night and Betty and Barney are together, and then there's Wilma. And all of a sudden, Barney's got an eye for Wilma. She's like, homewrecker! And Betty gets upset. I've never seen Betty upset. She's pretty upset. So what happened is that Betty has been replaced by that red-headed devil, Wilma. And what we call that is one thing was replaced. It's a single replacement. You will sometimes see that said as single displacement. It's a synonym. It means the same thing, so don't let that bother you. So one thing has been kicked out and replaced with another. You've done this. You did this with the either-or lab. We put aluminum into a copper solution. It's blue. So copper's in the solution. The aluminum I set down, and then the copper switched places with the aluminum. Now the aluminum went in the solution, and when you came back on that Monday, you had that really furry copper wire. They switched places. That's a single replacement reaction. A great example of this is not railroad work, but this is a great application for it. They're making thermite, which is another big AP final project that kids do. And what you do is you take iron trioxide, you react it with aluminum, and what happens is the aluminum and the iron switch places. And I tracked this so you can kind of see this. And the iron is kicked out and the aluminum is now in to the compound. And because of that, that makes molten iron, and it's pretty sweet. Very, very hot. If you don't, you shouldn't do it inside ever. If you ever did it inside, you need a big bucket of sand below it, because teachers who haven't done that, it will burn right through the table, right through the floor. If they're on the second floor, it will go to the first floor, so some kid desk, hopefully not their head, will also have molten iron falling down on it. I understand that some of these, this one is, but some of them are not balanced. Well, no, this isn't balanced. I'm not trying to balance these right now. I'm just trying to have you visually see and tracking those elements. So that's single replacement. So this will make a lot of sense then. What if you have 2 couples, and they're on ABC's wife swap, or whatever it's called, and they switch places, right? So now they both have a new partner. That is called a double replacement reaction. So 2 things are switching places, not just one. So an example of this is when you take some Rolaids, an antacid. You have some heartburn, and you have just a little bit too much acidity in your body. So it will neutralize the acid. And how is that done? Because the H, the hydrogen, and the sodium switch places. Okay? So the acid, stomach acid, is combined with the sodium carbonate, and what is made? Well, this is called carbonic acid, which immediately breaks down, by the way, into water and CO2. So if you took this, you'd probably burp a little bit. And then it makes a benign salt, which is table salt. But notice how they switch places. The H is now with the CO3. It was with the Cl. The Na was with the CO3. Now that's with the Cl. So they just switch places. And you're going to get really good at this really quickly without recognizing it. The last one, last but not least, the first 4 are more related to each other than this one. So what I did here is I have part of a working engine here, and oxygen can come in, oxygen can come out, fuel. It's all related into this reaction where you react in this case, a hydrocarbon, translation carbons and hydrogens, gasoline, with oxygen. In middle school or wherever, you've probably done this with a candle. You put a jar over it and it stops burning. Well, it ran out of oxygen. And it always makes CO2 and H2O. Well, that is called a combustion. In a combustion reaction, you might have heard of an internal combustion reaction. You're always, this is what's nice about this. Students make this one the hardest one when this one is the easiest of all 5 because all you got to do is place the unique compound here and then it's always reacting with oxygen, always making CO2, always making H2O. Always. So you're like, well, what does it make? CO2 and H2O. So one of my favorite things to do, go around my neighborhood and take pictures of grills. No, I like to grill. And that tank down there, what's that filled with? Propane. Propane is a hydrocarbon. It's C3H8. But check out the similarities the rest of the way. You're like, whoa, it's the exact same other 3 species in that equation. Yep. Because that's what combustion does. And it can be delicious. So, that all being said, we're going to use that today to help us determine some reactions. So we're going to do 3 of them. So if you would like to get out your other sheet, and we're going to put it sideways, and we're looking where the ball is on fire and the warning sign, and then we're going to be filling out the tables in the lower right on that sheet. Let's put our name on it right away so we're ready to go. You might want your orange sheet out, just so that you have access to it. Oh, so following up, I apologize. You have the ability to have some extra credit if you like. So like what it says, I don't always care about my grade, but when I do, it's the end of the quarter, and even though I didn't do all the assignments, I'll ask for extra credit. Now, please, again, always be mindful. If you miss extra assignments, hey, I missed 45 points of assignments, but I'm waiting for that 15-point extra credit. You're still down 30 points. Take care of your actual business first. It affects your grade on a greater scale than doing some extra credit. But what you could do, if you want to make a note on this, by Monday, you can make a poster. I do not want it any bigger than 2 pieces of paper next to each other. Do not come in with a big poster board and big, huge presentation. Oh my gosh, it's way too much. And if you want to do a single poster of illustrating a synthesis decomposition, a single, a double replacement, or a combustion reaction, you can get extra credit. 10 points for just standard effort, 15 if you go really crazy with it. It can't be like on loose leaf with fringes and all that stuff. So I mean, here's some examples. A is cutting in on B and C. Now B is kicked out. Oh, shucks. And now A and C are dancing. You could do it on the computer. You could find a picture of Selena and the Beebs. And then you could have the Weeknd over here. And then the Weeknd and Selena, and then the Beebs by himself. And then I just did a single replacement reaction. Or whatever. So, it's got to be yours. It's not something that you clearly just copied off of Google Images. We know which ones are on there. There aren't that many. So it's like, oh, I just used this one. You can see some other ones. Here's a bad-looking bird, ate a worm, synthesis. Now, I think he ate too many worms. But maybe you want to be a bouncer bird. I don't know. Work at the club. Needed to get a little bigger. So, if you like that, it's due by Monday. Take advantage of that stuff. I graded 3 of my kids in my tour last semester would have gotten an A- or an A, depending on the grade, if they had just done 1 extra credit report. They were that close, but they didn't do it. So that was a shame. Okay, so let's have our lab sheet. There's something that's really cool that you're going to start doing on Friday. It's called a splint test. You don't have to write this down, but this is in your lab everywhere. We need to be able to identify compounds. So if you look at this, you can see it. Like, I can see this compound, but you can't see gases. So how do you know what gas is present? And sometimes reactions have all of these in them, C's and O's and H's. So what we do is we light a splint. And a splint is what we use as just a coffee stirrer. And you light it, and if this is like a test tube, and I have it upside down and a reaction happened, I can put it into the test tube. And if it goes out, then CO2 is present, because CO2 will smother that flame. If I light it and I put it in and it burns brighter, it just keeps burning, it could be oxygen. And if it then it could have hydrogen, because that's flammable. And for some of you get a little gun shy because you don't know which one just whooped across the other side of the room, and you're like, is this the demo that I'm doing now? And you do it. Others of you, please let me. But it's fun, and you can figure out the type of gas just simply by putting a flame by it. So we're going to kind of do that today. So we're going to do some demos, and I'm going to show you how to write all this up. So you're going to have to be engaged with me here so you can kind of understand how this all is working. So first, let's talk about the fact that each of your demos on Friday, will have a description. It says it on the right side. It says reaction A, reaction B, reaction C, reaction D. So this one, though, is over by the ball that's on fire. So it says mossy zinc is placed into hydrochloric acid. We tried to underline some things. So mossy zinc, don't let that confuse you. That's zinc. So write that down. I'm doing this all. I'm showing you how this is all kind of working out. You got to make observations. So I know it's a little dark up here, but if you look, that kind of is a dull gray. So that's what I'm going to write underneath this part. What state of matter is this? It's a solid, right? So we put that to the lower right. Final question. Whenever I write an element by itself, I have to ask myself, is it a diatomic? So you might have learned some different ways, and they're all really effective. Whatever works for you is the best. We learned 7 of them. So you can do some really kind of goofy things like Mr. Brinkelhoff, or sentences like Hal never orders French Italian clove bread, and you're like, what? There's 7 and 7, where you make the 7 right here starting at 7, and there are the elements besides H. You could say heck no halogens, it's HNO and then all the halogens, but regardless of which one I come up with, Zn is not one of those diatomics. Okay? Second part, it says place into hydrochloric acid. So I have my hydrochloric acid right here. And I look at the label and it says, oh my gosh, it says HCl. So I'm going to write HCl. What's the color of this, if you can even tell? Here, I can. What's the color of that? It is. There are 2 words that you're trying to maybe say, and one of them is not right when I say color. It is clear, but I could have a clear red solution, right? I can see through a red solution. This is a colorless solution, okay? Is that a liquid? Does that look like a liquid?
Yes.
Okay, don't write that. It says solution. So I need you to start knowing today that AQ means a solution, aqueous solution. So this is colorless. And then it says which produces a gas. After collecting the gas is ignited. If it is non-reactive to fire, it is chlorine. If it's reactive, it is hydrogen. Fill in the chart. So we have to do this now. So what I'm going to do is there's only one way to collect the gas, and that's to put it in a container. So I'm going to collect it in a balloon. So I'm going to drop in a bunch of pieces of zinc. Ones that actually fit. Now we need to make observations. So what's some evidence of a reaction? There's 4. You wrote them on your sheet. Gas. So write gas produced. I don't see heat or light. Okay. I don't see a precipitate, but is that getting hot? So it's starting. It'll get hotter and hotter. That's actually pretty warm. So heat. You can write that. So where am I writing that? I'm writing that to the right for my observations. So what we need to do is figure out what's in here. If I light it and nothing happens, it's chlorine. If I light it and something happens, it's hydrogen. So let's find out. Well, here, let's make sure we have enough of it. If you're wondering if that's a color change, that's more of the zinc just getting obliterated into little pieces. As that settles down, that won't really be changed much. It's still getting bigger. That's good. Good. That's really hot now. I can't touch that very long. Okay. So what I'm going to do is oops. Pop. Doesn't mean a boom happens. It just, the boomstick has to come out when you want to try to light something. So, I'm going to turn off the lights. I just want to zoom a little bit away from the balloon, but on it, that'd be awesome.
Maddie.
I think something happened. So, what does that mean? What's present? Hydrogen is present. So, hydrogen's made. So what type of reaction does this look like already? Look at, hydrogen was with here, now it's kicked out. So what type of reaction do you think this is? Look at your 5. Single replacement. It's imperative that you figure that out as you're filling this out, or you won't be able to determine what type of reaction we have. Now, if that's the case, who's taken hydrogen's spot? It's the one that's by itself. So zinc goes in because hydrogen got kicked out. So here are 2 things you need to think about. 1, every time you write an element by itself, you have to ask yourself, is it a diatomic? So is H a diatomic? Answer is yes. And that is a gas. Second, every time I make a new compound, I have to check the charges. So Zn, that's one of those that you had that memorized, is a 2+. Chlorine is a -1, so it's ZnCl2. And I'll just tell you now, this one just takes a little experience, but use it this way. If you're confused, it's switching places, like it's going into, if you don't have any other information, into the other state that it was. So acid was AQ, the zinc is dissolving in there, so you can assume that they switch literal places, and that is an AQ solution, aqueous solution. So what do we have to do still? Last thing always, we have to balance. Balancing, I don't need to see the work. Usually this is pretty straightforward. You pick one element that's not balanced. I see the H's that aren't balanced. So there's 2 on the right. I put a 2 on the left. Again, nice little reminder. Make sure you're leaving just enough space to fit numbers in there. And does that take care of it?
Yep.
It actually does, because it takes care of the Cl as well. So that is a completed problem. So that works out. All right, let's move to number 2. Oops. All right. Now I hope this one works. Every hour that you do this, sometimes it's too close to the previous one. It doesn't always work as well. But we'll try. So, it said liquid methanol is placed in a large jug. So it already said it was liquid. So I have it right here. What color is this? Colorless is correct. That was a lot. Luckily we can use it for some other things. So what I'm going to do is actually spread this out. And I want it to slowly evaporate and get it full of the gas. And it says, is placed in a water jug filled with oxygen gas. So I want to write that in. Do I know anything else about that? Every time I write an element by itself, I have to ask myself, is it a diatomic? Is that?
Yes.
It is. So that should be O2. So, by looking at that, first off, colorless. What type of reaction is this? Take a look at your 5. This one's actually in the beginning hard to identify, and then once you get used to it, it's not. What is this one? Synthesis, decomp, single, double replacement, or combustion?
Combustion.
It is combustion because I'm taking a hydrocarbon, C's and H's, and I'm reacting it with oxygen. So what are my products? We already know it.
CO2.
CO2 and H2O right away. Now I don't know the states of matter of that, but I'm going to guess one of them. Only because to get CO2 as a solid, you need it to be very cold, and get it to as a liquid, you need to have a lot of pressure. We're not in those conditions. Okay. Oh, this is enough. So I dump out the excess. I put this way over here so it has no chance to react.
I'll make these on fire. Just like some of these. One pot.
You can go. So this is going to react with the oxygen in the bottle. That's what I was afraid of. It's still cool, but you can see the liquid layer or of oxygen. Ta-da! That was very artistic. Last hour, it went whoosh, and it all ended really quickly. The problem is this still has moisture in it, and it's not as filled with oxygen. This is extremely hot right now. I can't even touch it. Because it wasn't as of a clean burn. So what are my observations? I saw light, right? And there's definitely heat. You can believe me on that one. I can't even touch it. I was afraid that was going to happen. So heat and light. We said it was combustion. Now, water is a tricky one. I know there's not ice, so this is not a solid. I mean, that's clear. But you saw that the liquid came out, so that is evidence that there's liquid water there. That really was hot. So that's my combustion reaction. What I'd like you to do while I set up the next one is try to balance this and be mindful that there is an O hidden in there, okay? So you work on that while I get this next one set up.
3 on this, there's 3 O's. No, we need these. Wait, roll. 2, 4. No, this is O2. Your H's are down here. Because it's 2 here, and there's only 1 O on this side. Yeah, I am right. Yeah, I bet. So try to get you a sign. Yeah. You said hit me.
All right, we're moving on. So if you didn't get that balance, you'll have some time.
I don't know.
All right, the last one today is one of the cooler compounds. It's very dangerous. It's carcinogen. It's not good in a lot of ways, but it's very brilliant in many other ways. So let's talk about what the formula is first. If you use your polyatomic ion sheet, you can figure this all out. It says ammonium dichromate. If you're working on balancing, stay with me here. So ammonium on your sheet is NH4+. Dichromate is Cr2O7 2-. Everything I just said is on your orange sheet. It's not because I'm the chemistry teacher and I know. It's there. What do we do with charges? We crisscross them. When you crisscross to a polyatomic ion, you need parentheses. So it should be NH4 2 Cr2O7. Let's take a look at what it is. I think this is one of the coolest, most brilliant colors that you'll ever see in nature from a compound. So check this out. It's this bright, bright orange. It's very brilliant. It looks like your sheet. So first off, that's a solid, correct? I hope we all agree. Okay, so let's write an S and then make an observation. It's orange. It's like orange crystals. Oh, shoot. Did the second one, did we say applied heat? Okay, what do we need on the last one that we just had? When we say apply heat, what do we need? You need a triangle on top of the arrow. So in your second one, I apologize, put a triangle on top of your arrow. No, you can write the word heat, you just don't have a lot of room, so I would just do that. All right, so orange. You can write crystals if you want, but it's orange for sure. Okay, so let's talk about what this reaction is already. That's all I have. So if you only have one reactant, what type of reaction is this? I'm hearing the beginning of all these concepts.
Single replacement.
No, single replacement would have one thing by itself and two. What?
Oh, yeah.
Exactly. Decomposition that breaks down. Gotta be from Europe. So this is going to break down into multiple things. So what I'm going to do is I'm going to take a piece of paper towel and I'm going to make a little wick. And I'm going to dip it into some methanol that's flammable. All right. So remember what it looks like. Here we go.
He beamed us.
That is a first for me. Oh, here we go. Check out what's happening. What? The reason why I have the glass shield up is just to help contain it. I don't know why they call this a volcano reaction. I'm still trying to figure that out. All right, so let's take a look as this is finishing up what is made. Now, I don't expect that you would have known these products, but if you were given them, you should be able to figure out some information. So we could have conversations about, it's still trying to burn through, oh, there we go. Conservation of matter, be like, whoa, it made more. You can't make more than you started with. So then we could talk about the properties of this powder versus the crystals. Maybe one weighed more or less. You can't make something out of nothing. But looking at the information I have, let's talk about the three products that, again, had to be told to you. So I have chromium 3 oxide, nitrogen, and H2O. Which one do you think is that green powder? Just common sense. Which one of the three? The chromium, right? It's not nitrogen, and that's not any water I want to deal with. So that, to me, then, is a solid, right? So let's talk about a few things. First, I saw heat and light. Well, I guarantee it's hot. But I saw light or fire. You could write fire. I mean, you could write all sorts of stuff. You could write volcano. I mean, it's your observation. But then, this is green. All right, that's a green powder now, or close to it. What do you think the state of matter is in nitrogen, N2? It's a gas. 78, 80% of what you breathe is nitrogen. You're not breathing in chunks of June bugs that are called nitrogen. They're gas. And then H2O. Again, I know it's not a solid, because that doesn't make any sense. This is not chemistouine, so solids can't exist when there's heat. So it's either a liquid or a gas. And if you look closely, if you actually inspected this, I don't see any water anywhere. The paper towel doesn't look wet either. So remember that water can be a vapor. So it's gas. So we need to balance this one. So don't balance everything at once. Balance something that you need to. What is the thing I don't want to balance? Oxygens. Why? Because it's in more than one. So I just pick, oh, CRs are balanced already, and there's 2 of them already. Oh, H's. There's 8. There's only 2. So it makes sense to me that if I put a 4 there, that gives me 8 H's. On the right side, I have 3 plus 4 is 7. Look at that. On the left side, I have 7. And I'm good to go. So, going into Friday, you need to be able to fill out equations, or data tables, like we just did. And knowing what a reaction looks like and how it behaves from left to right is everything. So I want to quickly, this is a short one, go onto your little half sheet and just show you what and how this will apply to you. We are starting to take things away from you. So on equations 1, we told you every step. In this labette, we're telling you every step. But in this one, it says write a chemical equation for the synthesis of potassium bromide. If you're not sure, here's a good piece of advice. You put an arrow in the middle of your paper. You don't pull it on the left or on the right, because I need to have reactants and products. So if you have no idea, put an arrow in the middle and then see what you can do. If it's a synthesis of KBr, is that going to be on the left or the right? Synthesis, if you look at the type of reaction, you're making one thing, right? So that should be on the right side. So I'm going to write KBr on the right. And that's all we told you. Okay, you take a breath and go, well, what does that mean? Synthesis means that it takes multiple items and it makes one. So what could it be made from? Probably, because it's only 2 elements, K and Br. You might have to be told extra information otherwise to be able to figure that out. Every time I write an element by itself, I have to ask myself, is it a diatomic? Which one's a diatomic?
Bromine.
The Br. I'll give you a big hint. If you finish an equation and you don't have to round, you better double check everything. You probably did it wrong. I'm not saying that every equation needs to be balanced, but if you don't have to do it, you're very lucky, or you didn't check all your compounds. So then I have to balance it. The BRs, I hope that this is pretty clear, is a 2, and then I got to go clean up my mess on the other side and fix my case. So, today balancing equations due. Tomorrow we're finishing up equations 1. Keep your lab, that's for Friday. The whole back side has 4 tables that we just did. Those you're going to do in lab and fill it out the exact same way that you just did it with me for those other 3. Okay? So Friday should be a lot of fun. Just don't lose it. And that is it. So, you guys have about 5 minutes if you want to be finishing up balancing equations or equations 3.
Okay, how did you balance the second one?
I don't know, how did you balance the second one? Anybody get that balance? No. No? You can turn it off. Well, let's see.